experiment number 9. Determining the molar mass, kind of like we did with our hydrated salt, but a completely different method. Also, this is not a hydrate. This will be an unknown liquid. Let's choose number 1. But again, your instructor should have a bunch of sample data for any of the unknowns that we have. Now, this method is known as the Dumas method, and it relies on some very, very, very careful measurements. So I have for us again the expensive balance. You can see it over here, right, which reads to 4 decimal places. Angle our camera a little better. There we go. All right? So let's begin. First of all, it says to weigh a clean and dry Florence flask. This is what a Florence flask looks like. It's flat on the bottom so that it will stand up, even though it looks around. It's got a flat bottom. All right, and it says along with a small piece of aluminum foil, which we will use as a cap. So I have a roll of aluminum foil. If someone in your family calls it tin foil, then they are older than I am. We don't need a very big piece, but just enough so that it covers the top of the flask. Hot plate is not on yet, but not too much excess. So I have a little piece there that's hanging off the side. I'm just going to remove that because I don't want any extra hanging down that water might condense on. All right, so that's a Florence flask with a cap, and there we go. All right. So I'm going to record the mass of this Florence flask from the balance. And if you can read the balance along with me, you can see that it is not readable. 55.2649 grams. 55.2648 grams for our Florence flask and our cap. Great. Record that on your data sheet. I'm going to put a few milliliters, take the cap off, put a few milliliters of my unknown into the bottom of the flask. All right, just a couple. Enough where I can see that it's in there. Remember, gases expand massively upon heating and vaporizing. So it doesn't take much to fill this flask with gas, which is what's required. We're going to find the molar mass of this unknown, and from that, hopefully, determine its identity. Really does not want to go back on. I can't rip this anymore. It's just my glove that's ripped, not the cap. Put on a new glove. I can't rip this and lose any because I already weighed it, right? I don't have to weigh it now. I got a few milliliters in there. I'm going to take a pin and punch a few holes in the top. So I have a few milliliters of my volatile liquid, meaning it evaporates readily, even at room temperature. I have some pinholes in the top to allow the vapor excess to escape. And I have a few boiling chips in my hot water. Now, the water, if it was boiling, would actually make this experiment a little bit more challenging because the bubbles coming out of there would make it really hard to see when exactly all of this liquid has evaporated. And that is the key to this lab. The liquid must exactly evaporate. There can't be any left that hasn't evaporated, and I can't keep heating it after it's all evaporated. Otherwise, the gas will keep expanding, as you'll learn in Chapter 5, gases. And then when I take it out of the hot water, the amount that recondenses won't be the amount that exactly filled the flask because it will have expanded in the flask. So I have water here, and it's been heating for a little while. I only had the hot plate set up at 125 this time. But let's take the temperature of the water using our old pal, the temperature probe. All right, so not touching the side again, not flipping over my Florence flask either with the cord. Move it out of the way. All right, so we're still rising, still rising. I could just leave this in there, in fact, if I wanted to, because I want the temperature of the vapor inside that flask, which is going to be the same as the temperature of this water. So I'm just going to leave it in there, and we'll double check it when we've finished. Now the challenge is I need to get this Florence flask submerged as deeply in this water bath as possible. I may or may not be able to fit this temperature probe in there at the same time. Let's see what I can do. All right, so clamp that on there. And submerge as deeply in the water as possible. Now, the challenge is, if you look at this thing, even really close up, it is very hard to determine, is there any liquid in there in the flask or not? So if I jiggle it, then I can kind of see inside the flask that there's still liquid in there. My challenge, and yours if you were doing this live and in person, would be to determine exactly when all of the liquid in this flask has evaporated, and not a second longer. If I don't let it evaporate long enough, there's going to be extra liquid in my flask that shouldn't be there. If I heat it too long, once it evaporates, it's going to overfill the flask and extra is going to come out the top. I don't want that. I have to get it exactly timed right. Because what I'm looking for is the flask to be filled with volatile liquid, vaporized volatile liquid. I'm going to take this thing out of here really quick and let it recondense back to room temperature, and then weigh it. And I'll see how much more the flask and cap weighs with that extra little bit of liquid in there. And we're talking less than half of a gram of liquid, because the vapor that fills this flask is only like a 140 milliliter flask. It doesn't take very much. So let's see if I can do it. I'm jiggling it, and there's definitely still liquid inside that inner flask. See it? Now I know that it is vaporizing, A, because it's a volatile liquid, B, because I saw some in the neck of the flask. It was condensing in this neck at first. I could see it before. That's why I want it submerged as much as possible, so that the whole neck is hot too, and it keeps it evaporating out of the flask. Now again, I could have the water boiling, and this might vaporize faster, but it makes it a whole lot harder to see. This water is at 51.3 degrees. 51.2 degrees. Nice holding steady temperature. Which might not be hot enough to do this quickly, but we'll get it done. Still a lot in there. You want to have too much in the flask, otherwise this can take a while. So maybe I will increase my temperature. Try and get this going a little bit more. Regardless, I want to look at the temperature right when I take it out, because that is the temperature of the vapor. Still some liquid in there, as you can see. Also, the jiggling would help if, since I don't have boiling chips in the Florence flask, that can help to make sure that it doesn't just suddenly shoot out the top. I splash water out of the flask onto the hot plate, no big deal. Just got to make sure that I don't splash it into my face. It boils away. Still quite a bit of liquid in there. I can't remove it too early. I can't remove it too late. As we're approaching the end, I'll put the camera back on the tripod and also get a wet paper towel so that I can quickly cool, but also dry off the outside of the flask. My water temperature in the water bath is now 54 degrees, slightly increased. You can see that there's definitely getting to be less liquid in my Florence flask. All right, so I'm looking really carefully. There's still liquid inside my Florence flask. Temperature on the hot plate might not be hot enough. I'll crank it up. My water temperature is only at 56 degrees. So if this was alcohol in there, those boil at 70 something. Acetone boils at 56. Liquid in there isn't boiling, but it doesn't have to. Remember, it just has to be volatile. It just has to evaporate and fill the flask with vapor. But there can't be any liquid left. So a lot of people, when they do this quickly, just boil the water. Again, that makes it very, very challenging to see when all of the liquid has disappeared. While we're waiting, we can check the barometric pressure of the room, which should also be the pressure inside the flask, since the flask is open with those holes to the atmosphere. And according to our little barometer, we've got 29.91 inches of mercury. Now, you know, if you watch the weather or see weather on your app, weather app on your phone, and it's got 29.91 little quote mark. That's inches of mercury, because we're in the United States and we refuse to go along with the metric system. And so if you convert millimeters of mercury from inches of mercury, which they even put it here on the barometer, if you multiply the millimeters by you multiply the inches by 25.4, that will give you the number of millimeters of mercury of pressure that's going on in the atmosphere. Regular atmospheric pressure is 760 millimeters of mercury, which is somewhere around 29.9 inches of mercury, but we'll want to do it exactly. So 29.91 inches of mercury, convert that to millimeters, and then you'll need to convert that to atmospheres, because the gas law that we use for this experiment, the pressure must be in atmospheres. There is still liquid in that Florence flask. This is why you want to minimize the amount of liquid that you use in this experiment. Our temperature of our hot plate is well over 100, but our water in the beaker is still only 62.7. All right, so we're getting close. Let me show you up close and personal. Inside the flask, you can still see there's definitely a little vapor, not vapor, there's a little bit of liquid in there. There's definitely less. We're getting close. When it's exactly all gone, I'm going to take that flask out and I'll hit it with the wet paper towel to cool it rapidly, and we'll see what happens. So this has been around 20 minutes so far, and this is the point at which students generally get really impatient and really frustrated. And then the sky gets angry and there's a huge peal of thunder. And so they just take their flask out too early with their liquid still in the bottom of it, and it blows the whole experiment. You get crappy results. Or they get bored and they stop paying attention and they look back and, oh, the flask is empty, and then they take it out and they continue, and then there's no recondensed liquid after they let it cool. Well, paying attention is another one of those job skills that you're picking up in here. I still have a minimal amount of liquid in my Florence flask that I must wait for evaporation. Volatilization, gasification. Close though, real close. Remember, there's only going to be a drop of liquid that will have recondensed from the vapor filling this flask. This flask is not that big, around 140 milliliters. We'll measure the exact volume afterwards. But it doesn't take much gas to fill 140 milliliters. Remember, 18 milliliters of water fills up 22.4 liters of gas. 18 milliliters of water turned to gas fills up 22.4 liters. 140 milliliters, 0.140 liters. It's not very much gas. Oh, we're close, very close. Now I do have some vapor in the neck, but I'm hoping that it's just water vapor on the outside. My water temperature is 76.8. Very close to the end now. A little splash. That's what safety goggles are for, and gloves. Very close to the end now. Water temperature is 78.4, which was also my gas temperature inside the flask. If you used a 600 milliliter beaker, this would take even longer because there's so much water to heat up. Water absorbs a lot of heat. That's why they throw it on fires. It's really useful for lowering the temperature of a flammable solid. Still a couple of drops in there. Got my wet paper towel ready to cool the flask. My dry paper towel ready to dry the flask. Still a drop, 2 in there. Anticipation. Water temperature is 83.8. Still rising, which means our gas temperature in here is also still rising. That's it. There's no liquid left in there. I'm going to quickly raise this and hit it with a wet paper towel. It can be a little bit dangerous because we really don't want to shatter our flask. Moving it away from the hot plate over here. Put it down where you guys can see. A wet paper towel to rapidly cool my flask. As I do so, 85.1 was my water temperature, which means that was the temperature of my vapor inside the flask. As I cool this flask, just using the wet paper towel to absorb some of the heat, you can see, in here is now a drop of liquid. That doesn't mean I did the experiment wrong. It means I did the experiment right. There was nothing in there when I took it out. No visible liquid. Now I have a drop of liquid. What's it from? The flask being filled with vapor that has now recondensed. This is not a big flask. It's not going to be a whole lot of liquid, right? So I've got it now. Just trying to cool it a little bit more. If I can weigh it at room temperature. No idea what I wrote down on my data sheet before for the number. You can certainly check. Dry the flask. There cannot be any water on the outside of the flask. There cannot be any water stuck to the cap. I can't forget to weigh the cap, right? All of these things will change our mass drastically. And remember, all I'm looking for is the mass of that little drop that recondensed in there. My hands need to be gloved so that I'm not leaving fingerprints all over my flask. So let's weigh it. Balance was at 0.000. We're at 55.4349. 55.4341. That'll be our final number. 55.4341 is our final value, which should be a drop more than what we started with. 55.4341. That little drop is our recondensed vapor. That plus the temperature that we wrote down, whatever it was, 85.1, I believe. We'll have to convert that degrees Celsius to Kelvin because our math requires our temperature to be in Kelvin. We will convert our pressure of 29.91 inches of mercury to millimeters of mercury and then convert that to atmospheres. All of those, the mass, the pressure, the temperature, according to the ideal gas law, will give us number of moles of our compound that this drop corresponds to. If we have grams per mole, those are the units of molar mass. And we will have determined the molar mass of our unknown, and then we can go to table 9.1 and look at all those molar masses between 18 grams per mole and 154 grams per mole. And whichever one's closest, that's probably what our unknown liquid is. So the creativity of this lab is we're looking for grams per mole. We can weigh grams if we can figure out the number of, the pressure, temperature, and volume of this flask and the gas in it, then we can figure out the number of moles because PV equals nRT. Pressure times volume equals number of moles times R, the gas constant, times temperature. The only thing that we haven't found so far then is the volume of this flask. And to do that, we need our old friend, the graduated cylinder. So I told you that this flask is around 140 milliliters. We'll need to measure that exactly. So I'm going to fill up the flask just with tap water all the way exactly to the top. No more, no less. Okay? My flask is completely full of water. Now, it doesn't matter if it's wet on the outside. This graduated cylinder only holds 100 milliliters. I'm going to have to use it more than once. So here we go. Don't spill any. Don't go past the 100 line. I don't need to go exactly to the 100 line either. Why waste my time, right? Get those air bubbles out of there. Still a few stuck to the side there. We can get those out without splashing. The challenge. Or we could just make a note. There's air bubbles in this thing. I bet our volume is a little bit less than what we actually measured to be. All right, so my first volume that I'm measuring is 92.7. 92.7 milliliters of water was my first volume. And I'm going to add that to the second volume, and I'll have my volume of my flask dumping in. Our second volume is 41.3. 41 point, well, let's get that last drop down in there. 41, yeah, still 0.3. 41.3. So the 41.3 plus the 93 point whatever I said, we'll add those two together. It's around 130, 140 like I expected for this Florence flask, which actually is marked on it. 125 milliliters, but it's around 125. It's not exactly. All right, so we now have the volume of our flask. We had the pressure in the flask because it's the same as the air pressure outside the flask. We have the temperature of the gas in the flask because it was the temperature of the water. And that will give us the number of moles of gas that was in this flask. We condensed that gas back down to a drop or so and weighed it, and we had the mass of that volume, of that pressure, of that number of moles. Since we had a grams and we had a mole, grams per mole, that gave us our molar mass. I hope you enjoyed the lab. It requires patience.